Nobel Prize in Medicine 2025. Trio honored for decoding the immune system's security guards. Stockholm, Sweden, October 6, 2025. The Nobel Prize in Physiology or Medicine for 2025 was jointly awarded today to Mary E. Brunkow, USA, Fred Ramsdell, USA, and Shimon Sakaguchi, Japan, for their groundbreaking discoveries concerning peripheral immune tolerance. The laureates' work unveiled the critical second line of defense that prevents the body's powerful immune system from mistakenly attacking its own tissues, a process known as autoimmunity. This revolutionary understanding of immune regulation has laid the groundwork for a new era of therapeutics for autoimmune diseases, cancer, and organ transplantation. The immune system's peacekeepers, regulatory T cells. For decades, the prevailing scientific belief was that the immune system achieved self-tolerance primarily through central tolerance, a process in the thymus gland where self-reactive immune cells are deleted before they mature. The work of the three laureates demonstrated that a crucial dynamic control system, termed peripheral immune tolerance, exists outside the thymus. The Nobel Committee praised the trio for identifying the immune system's true security guards, a specialized class of white blood cells now known as regulatory T cells, TREGs. Their discoveries have been decisive for our understanding of how the immune system functions and why we do not all develop serious autoimmune diseases, said Al Kemp, chair of the Nobel Committee. A three-part breakthrough. The prize honors a series of interconnected discoveries that began in the mid-1990s and culminated in the full identification of the mechanism. 1. The initial discovery of the suppressor cells, 1995. Japanese immunologist Shimon Sakaguchi, a distinguished professor at Osaka University, made the first pivotal finding. Challenging the existing dogma of central tolerance, Sakaguchi discovered a previously unknown subpopulation of T cells that actively suppress the activity of other T cells. He identified these suppressor cells by a specific protein on their surface, CD25. His work resurrected the long-dormant and often controversial concept of suppressor T cells, establishing the existence of a cell population that maintains immunological balance in the body's periphery. 2. The genetic key, the FOXP3 gene 2001. The next critical piece of the puzzle was provided by American scientists Mary E. Brunkow, an immunologist, and Fred Ramsdell, a molecular biologist. While studying a strain of mice with a fatal, rapid-onset autoimmune disorder called scurfy, Brunkow and Ramsdell pinpointed the genetic cause, a mutation in a previously uncharacterized gene that they named FOXP3. They then demonstrated that mutations in the human equivalent of this gene caused a severe, X-linked autoimmune disease in children known as IPEX syndrome, immune dysregulation, polyendocrinopathy, enteropathy, X-linked. This proved that the FOXP3 gene was essential for preventing the immune system from attacking the body. 3. Connecting the dots 2003. 2 years later, Sakaguchi successfully linked his initial discovery with the gene found by Brunkow and Ramsdell. He conclusively demonstrated that the FOXP3 gene is the master regulator that governs the development, function, and identity of the regulatory T cells he first identified in 1995. This unified discovery solidified the mechanism of peripheral immune tolerance and firmly established the importance of FOXP3-expressing regulatory T cells as the essential mechanism for preventing autoimmunity. Translational impact on modern medicine. The identification of regulatory T cells has had a transformative impact on modern medicine, giving researchers new, targeted approaches to treat a wide range of diseases. Autoimmune diseases. By identifying the on-off switch for self-tolerance, Scientists can now pursue therapies aimed at increasing the number or function of Tregs to suppress the rogue immune attacks seen in conditions like type 1 diabetes, lupus, rheumatoid arthritis, and multiple sclerosis. Numerous clinical trials are currently underway to use Tregs as a cell therapy to re-establish tolerance. Cancer immunotherapy. In the context of cancer, Tregs are often a liability. Cancer cells exploit Tregs to create an immunosuppressive environment that shields the tumor from the body's natural anti-cancer T cells. The discoveries have opened the door to new strategies aimed at down-regulating or temporarily depleting Tregs in the tumor microenvironment, thereby unleashing a more aggressive immune attack against the malignant cells. Organ transplantation. The ability of Tregs to suppress unwanted immune responses is invaluable for preventing the rejection of transplanted organs. By leveraging or enhancing Treg activity, researchers hope to achieve immune harmony, where patients can accept a new organ with fewer or less potent immunosuppressive drugs, which often carry severe side effects. Mary E. Brunkow is a senior program manager at the Institute for Systems Biology in Seattle. Fred Ramsdell is a scientific advisor at Sonoma Biotherapeutics in San Francisco, and Shimon Sakaguchi is a distinguished professor at Osaka University. They will share the prize money of 11 million Swedish krona, approximately $1 million USD.